Hello, everyone. Welcome to the Data Colada seminar series. My name is Joe Simmons, and I'm sort of filling in for Leif Nelson, he's here, but he's at the airport. So I'm doing all this and I might screw it up, so I apologize in advance. Okay, so today we're here for a talk by Yuri Simonsohn. He's going to talk about interactions, and we have three excellent panelists. So we have Pam Davis-Keene, we have Gary McClelland, and last minute we were able to get Yoel Imbar. Two other panelists unfortunately had to cancel at the last minute, so Yoel is stepping in. And then of course we're joined by Leif and Yuri. You can also turn on, okay. All right, Yuri.
I cannot share my screen, Joe, sorry.
You cannot share your screen.
Yeah.
Awesome. Okay. Let me try to fix that. Okay, you should be able to now.
All right. You can see it, right? All right. So thanks everybody for coming, and sorry about the panel last minute change. The title is Interaction Gate. I'll be talking about interactions. I usually start my talks with an overview of what I'm going to be talking about in a single slide. So let me do that now. We study interactions in a lot of our papers. In a recent review that I did, casual of issues, about 70% of papers include interactions, either as a primary or as a secondary analysis in the paper. And we usually start with a regression that has this form. And then we do one of two things, or actually we do two things with interactions. So first we test them. We ask, does Z change the effect of X? And we usually do it with the p-value of D. If you want to go Bayesian and compute a Bayes factor, a posterior, or credibility, it doesn't matter, it's the same point. We are asking if this is not zero. And then we probe them. I don't know how common this term is. Sometimes it's referring as interpreting. And the idea we want to say, okay, the coefficient of D may be hard to interpret. So what we do, we say, what is the effect of X when Z is, let's say, 3? And for that, we take the point estimates and we say, all right, so the effect of X is B, and it's also D times Z. So if Z is 3, we say that's the effect of X. Those are the two things we do. And usually those are portrayed graphically in ways that had multiple names, such as spotlight analysis, Johnson name, and flatlight. It has multiple names, conditional marginal effect. The problem is that nature is not linear. So the effect of X, the effect of Z, or the interaction between X and Z can be nonlinear. And the problem is, if any of those things are not linear, any of them, then we're going to have problems. And I'm going to be showing you this 2x2 matrix throughout the talk, where I'm going to be distinguishing between whether you want to just test the interaction or you actually want to probe it. Right? This is going to be harder to do, more difficult to get this right than to get this right. And it turns out, and I think this is a bit underappreciated, I'm not sure, but it matters a lot whether the two things that you are interacting are correlated or uncorrelated. It matters really a lot for how sensitive the results are to nonlinearities. So I'll be referring to this a little loosely as experiments. And what I mean by that is that X and Z are uncorrelated. So if you manipulate X, of course, it's uncorrelated with Z. And then when they're correlated, okay. So what happens? What happens if nature is not linear and we estimate a linear regression? If you just want to test if an experiment has an interaction, actually nothing happens. It's totally fine. If you want to probe it, however, it's bad. And if you want to test whether there is an interaction, even just testing when the predictors are correlated, it's really, really bad. And then if you want to probe that, it's even worse. Okay. So this is what I'm going to be doing, is talking about these four cells through the presentation. And my goal is not just to say, hey, these things don't work well. And part of the reason I've been working this for like 3 years is that what I've been trying to look for is, can I find a tool that will be very reliable, that can be applied to a realistic set of circumstances, and it will be valid, right? So what I'm referring to as curvilinear robust is not super catchy, but I think it explains what I'm after, right? That if you're interested in an interaction, you'll get the right answer, whether things are linear or not. And to give a motivating example of how nonlinearities change things and make things bad, let's think of age, weight, and gender. So this is how God made us, right? So boys grow heavier over time than girls do, but at first we start about the same until we hit puberty, basically. This is the first derivative of God, right? This is how the slope changes over time. That's so this is girls hitting puberty a bit before boys do. And this is what a social scientist would estimate if using a linear regression, right? Because they would fit a linear regression, and then they would do, in this case, this would be flat line, or this would be Johnson-Neyman. And what he would say is, this is the pound difference. So you would say, all right, if I'm fitting a straight line, I'm going to predict that baby girls are significantly heavier than baby boys. And a lot of our theory, especially in psychology, it's critical to know whether at some point the effect reverses. Like a lot of our theories are tested that way, and a lot of findings are most interesting when you get a reversal of some kind. And here we're seeing a false positive reversal of the gender difference in weight that is completely spurious and arising from the linearity. This is a motivating example. Okay. Why would we expect the world to not be linear? Okay, and so as social scientists, that shouldn't be a very hard proposition. It should be easy for me to persuade you that linearity is unlikely. And there are many reasons. I'll choose three. One is a lot of things that happen in life involve perception, and perception has diminishing sensitivity, not constant sensitivity. So any task that involves perception, you would expect it to become not linear at some point. And then economics tells us that most things have diminishing returns. So the more you work, the more effortful, the more costly the effort gets, the more you consume ice cream, the less pleasure it brings in the margin. So those things are not linear. And then a lot of things we study involve scales. And if even some people are at the boundaries of the scale, you don't need a ceiling effect in the way we traditionally think of it, where literally the mean is at the ceiling. If just some people are at the ceiling, which almost always there are some, those people you just can't move at all. And so as you move people to the right, unnecessarily you hit a nonlinear point, a nonlinear relationship. And so these are just arguments. This is me waving my hands loosely about the qualitative nature of the world. Here are just some examples from actual data sets. This is how age is associated with how conservative people become. So we get more conservative as we get older, but at a diminishing rate, at least we measure on this 1 to 7 scale. This is how people perceive themselves to be knowledgeable as a function of how much they actually know, how many answers they got correctly. This is actually a return to this, the relationship between antisocial behavior and how people performing a math test is not linear. And I'll return to this one too. This is a paper I had with Francesca Gino from years ago. This is how, and I will also return to this example. This is how students who apply for an MBA program were evaluated as a function of how much experience they have. So for MBA students, we tend to like them to have experience, but after you get 3 years roughly of experience, it doesn't matter anymore. So these are the kind of relationships we expect to see in the real world, right? And those are the kind of relationships that break the regressions that we run. What can you do if you're not going to do linearity? What can you do? So I'm going to think of 3 broad approaches, and I'll bring them to testing and to probing somewhat selectively. I won't be using them always. So one thing, and this people have been doing for a long time, and people have been correctly pointing out that doing this lowers power. But one thing you can do to avoid linearity is to have 2 points, because 2 points are always linear. So if you just have a median split, necessarily the association is linear. So you cannot violate linearity when you have a median split. So that's one thing you can do. It's going to have some benefits, and some of them are surprising. I should say a lot of the things I learned while working on this surprised me between a little and a lot. Some of the virtues of median split surprised me a little, I would say. And so what you do with this is you can say, all right, if I do a median split, I can give you the average for high and average for low without linearity violations affecting me in any way. Another thing you can do is you can add flexibility to the X and to the Z while keeping this linear. And there's 3 papers in the 90s. This, if you want to read up on that, this is my favorite, who talked about it. And they proposed just adding quadratic terms to account for any known linearities. I'll be looking at that too. And this turns out to be insufficient in some cases. So I try a stronger version of this where I immediately split the X. I do like a median split on X and a median split on Z. And I allowed the functional form to change before and above the median. It's like a very rudimentary spline, or a very rudimentary flexible fitting. And then you can go all out and say, I'm just going to estimate a fully flexible model where this is going to be not linear, this is going to be not linear, this is going to be not linear, whatever the data tells me. And there's a few options available. Actually, I see one of the questions was about this. There's kernel regression, there's lowest, there's the local regression. When just starting this project, I tried with a few of them, and something called the generalized additive model turned out to have the better properties. So I'll be talking a lot about GAM today. This ends up working quite nicely for the problems that we face as social scientists. So I think we should embrace this idea, which is, although it's new to most of us, it's really not that new. It's from the late 80s that people who were working on it. To give you a sense of how well GAM works and how we can expect it to perform, let's generate some data that's really not linear. Okay, so y is the sine of x, and then minus the linear term. So that looks like this. Okay, now when I add some noise to it, this is what the data would look like if you looked at it. You don't really know what's going on, right? So you would fit a linear regression and would say, the data is something like that, the real model, something like this, and then we'll give you some confidence band around it. And if you do GAM, it would do that, which it's kind of impressive. And obviously it's not magical, right? So it is fitting data. And at some point you could fit it in little enough data that it wouldn't get it, but it does perform quite well. And you can keep that in the back of your mind. If you're interested, I won't talk about it here, I don't have time. But in R, this is the package. The original, as I was mentioning, is the late 80s, the original work. And there's this textbook by Wood, who's also the creator of the package. The treatment is a bit technical, which is perhaps why we haven't used it so much in social science. For example, in economics, you see bean scatter becoming very popular, which is a very rudimentary version of this. I think we should start seeing, my presentation aside, it just seems like a very promising tool for social science. All right, so this is the outline. I'm just gonna go through the 4 cells. Why is it fine, actually, if things are not linear, like we saw before with all those examples? Why is it fine to just run a regression if it's an experiment? So in a nutshell, this is why. The regression, what does it do? The regression gives you the average slope. It just computes the average slope in the data. That's one way of thinking about it. And you can compute the mean, even if, quote unquote, people are different, you can report and compute their mean meaningfully. So some people are above average, some people are below average, and that's totally fine. You just report the mean. And just like that, you can also report the mean slope, even if the slope is different across different points. There's no harm in that. Let me give you a concrete example. Suppose you go on a diet and you lose decreasing numbers of pounds over time. So it's not linear. It's not 2 pounds per week or whatever. But the regression would say, you lost on average 3 pounds per week. And we will be okay with that. So even though it's not linear, that answer, right? This is a non-linear relationship. We are okay with this answer. We interpret it correctly, and it's useful. And for that reason, it's fine to run interactions in experiments, even if it's not linear. Okay, what about probing those interactions? Why is that a problem? Okay, so I'll spend some time on this, but I'll just give you the intuition right now. The average is not going to be the true value for everybody, right? Some people are above average, some people are below average. And when you probe, it basically assumes that everybody's average. So if we go back to our diet, if you probe a linear regression, it would say, oh, because the average is 3, you also lost 3 pounds in the 3rd week. And that's wrong. It is imposing that linearity, and it's leading you to say, oh, if it's linear, it's always the same. And as you project that away, you're wrong. So if we're not going to do linear regression to probe interactions, what are we going to do? Remember, we had those 3 options. We can discretize, we can add flexibility here, that's what the squares were, or we can do a fully flexible model. I'm not going to even look at this. I'm saying it's obviously bad for probing. Why do I say that? Because this remains linear. The interaction remains linear. And so obviously for probing, it's not going to work. So I won't even try it. So I'll try the very simple thing and the more sophisticated thing. So how do I use GAM here? It's actually, I think it gives a good intuition for somebody who's never thought about GAM before. It's still fairly intuitive to think about it. we're going to ask GAM to estimate what is the relationship between Z, the moderator, and the dependent variable. So let's say X is a treatment, and let's say Z is H, the moderator is H. What's the relationship between H and the dependent variable? And we do it separately for treatment and control. And then what's nice, we estimate those two. And if we look at the difference, what we have here is we have the effect of X for every possible value of Z. That's estimated by GAM. We have it, right? Because we have, this is the effect when Z equal 1 and X equal 1, we have this value. When Z equal 1 and X equals 0, 1, so we just subtract it and we have vertically that distance. We have a nice treatment effect for every possible value of Z. So it's very similar to the Johnson-Neyman procedure or the flat light or conditional marginal effect plots. I'm trying to remember what other names that procedure gets. We've seen procedures like that, but it's based on GAM. So I am creatively calling it GAM Johnson-Neyman. So that's going to be the proposed solution. Instead of using Johnson-Neyman or the regions of significance, maybe that's the way you know it. Instead of doing that, we'll just call it GAM Johnson-Neyman. Okay. So I'm going to do a horse race for probing the interactions. So what I want to know is, can we really do better with this than with a linear model in a variety of settings? And how would the median split do in that setting? Okay. So for that, I have a lot of real data examples coming up, but for this particular cell, I haven't found useful examples. I'm not sure why it's surprising, but a lot of the papers that do interactions that they probe don't post their data. I haven't found great examples here. So this one is going to be simulation, but I have real data coming up. So the question is, how do you quantify how wrong a probed interaction is? It's kind of a hard thing to say. Like if you say, oh, you said 3 pounds from week 3, but it's 2 pounds, like how wrong is that? And how do I compare when I'm making up data, right? So that was a challenge. So the way I'm dealing with that is I'm creating a hypothesis testing framework. So I'm picturing a researcher who's interested in testing whether the effect reverses at some point, but the effect does not reverse. And then I ask, how often do you erroneously conclude that it reverses? And so then I can express how bad or good a method is with a false positive rate that we're used to interpreting. And then the numbers are sort of scale free and we can sort of relate to them. Although there's necessarily some artificiality to the whole exercise, right? Because I'm generating data that captures what's going to happen in the real world in general. It's a hard thing to do. So there's a moderator and it makes the effect smaller, but it's never negative. So you can think this is one stylized situation. It would be, there's an effect, but at some point there's a ceiling. And so there's a treatment that it helps, it moves it up, but once you hit the ceiling, the effect gets smaller, smaller until it gets to 0, but it never flips. And you can make it more realistic by making it not linear. So I chose a function that has that shape, that it's similar, but it's more smooth. This may feel artificial, and it may feel like I'm sort of helping the median split by making things split at some point. So I'm doing that. And so I ask, I'm going to generate this data, and I'm going to estimate a linear model, and I'm going to evaluate it the way this textbook with 49,000 citations tells me to do it, which is I'm going to estimate it, I'm going to project the effect at 2 standard deviations. I'm going to see if it's significantly different from 0 in a negative. And this is from the 1930s that we have that technique. Or I'm going to do the median split. And I presented this before, and somebody asked a question whether I was choosing the data, perhaps unintentionally, that really helped this particular technique. So what I do is I dichotomize also the top third, so that if both of them perform well, then it's some insurance that it's not that I just happen to stumble on the functional form that's very good for median. And then I do the GAM Johnson-Neyman. I haven't had any questions. Is this clear? Am I going so far so good? Do you have any? Joe? No questions? All right. So I'm going to run the horse between them. I try to avoid sort of stumbling on data sets that really help one technique. I try to vary it in a way that's outside my control. So I take X and I make it either normal or skewed left or skewed right or uniform. And I vary how severely attenuated the interaction is, the sample size, and how much random noise. So for each of those 2 big scenarios, I have 36 variations, leading to 72 variations. And for each of them, I run about 5,000, and I ask, how often do I incorrectly conclude that there is an interaction? Sorry, that the effect reverses and becomes negative when it's in fact always positive or zero. This is just previewing the results for what's coming. All right, there's a lot of information here. So let me walk you through it. This is just the ceiling, and behind the blue box is the more smooth function, right? The smoother function. This is to remind you of what that looks like, right? So that is one scenario. I run 5,000 simulations, generating 5,000 sets of gray dots. And then I run a regression, and I got the interaction, and I projected 2 standard deviations above zero, and I asked, above the mean of z, sorry, and I asked, do I get a negative effect of x that's significant, even though it's never zero? And that happened always. So the linear model always got that wrong. And I'm sorting here by performance. So this is in the very best scenario that I generated, right? Maybe it was left skewed with a small sample and little attenuation. It doesn't really matter. I'm just trying to cover the bases rather than estimate. Yoel, you were gonna?
Yeah, I have a clarification question from the chat. This isn't a faux experiment, right? So you have a dichotomous manipulated predictor and then interacted with a continuous. That's right?
That's right.
Great, thank you.
Yeah, because I mean that first cell that it's still in the top row, which is experiments.
Yes, thank you.
All right, and then
I'm going to take a risk and try to speak here. My intuition would have been that the furthest left data point on any sort of figure like this should be at 5%. The fact that it's not at 5%, should I interpret that as there's a massively inflated positive rate? The figure in the top left. So the red dot.
This is terrible. It should be, the false positive rate should always be 5% or lower.
But in yours, it's never 5%. Like right, that would suggest that there's no scenario in which the testing interaction is fine.
There's no scenario within the set that I simulated. And that set is, there is an interaction, but it ceases. If I had done, for example, a linear model, if I had generated a linear model, the false positive would be 5%. If I had generated a model where I had very little attenuation, so that even as you project, even if you overshoot, you don't quite go to negative, you wouldn't. If I wanted to show, this is not my assessment of how bad the linear model is in reality. This is a stress test of, can I find a tool that will work well when the linear model performs poorly? For me to say the real world is like this will require me knowing to what extent the real world kind of looks like that. And I don't know that. I don't think anybody knows that, right? Like to what extent attenuation in the real world so strongly deviates from linearity within the range of observed values that we predict sign reversals that are absent. I don't think anybody knows that. And so that's not my point is not, isn't this amazingly high and that's what happens in real life? My point is, isn't this amazingly high? And look, this all nail it. These are all perfectly fine solutions. So if I could think of a way that would make these lines perform worse, I would produce them. I haven't thought of a way that would generate that would make the GAM systematically wrong or the dichotomized one. Okay, so let's go back to the red. This is the false positive rate. The very best case scenario that I consider was 20% false positive rate. It goes all the way to 100. I did robust standard errors, because this part of it could be when you have specification error, the standard errors can be wrong. And so that's why you robust standard errors, and that doesn't really do anything. And then all the other techniques push it below the 5% line. The reason why it's below it and not at it is that I am asking, is it negative? So I'm doing a directional test, but I'm doing it with a two-sided. So the correct false positive rate should be 2.5, which is kind of what you get for the majority of points. Now, one line that I want to draw your attention to is the cherry pick one, because I'm going to be proposing to people that they run a GAM Johnson-Neyman. That's what I'm proposing, but that's complicated. And I'm saying, well, the median split, that's fine too. So what I think is going to happen is people will do median splits, and if it looks good, they're done. And if the median split doesn't look good, then they'll read up on how to do the GAM, download the right package or whatever. So I'm asking, what happens if people do that? So if they p-hack by choosing between those two, and yeah, technically, sometimes they get a little bit over 5%. But if we compare that, that is a massive improvement. I think we can live with a 6% false positive rate after 80 years of, up to 100% in those scenarios. And then basically, if you make it smoother, it's the same picture. Nothing really changes, so I'll move on unless you have. Okay. So what about power? So I'm saying this is about false positive rates. What about power? So I won't show you details, even in the paper. I have this in the supplement, because I think really it's the bottom line is all that matters, I think. So Gam, Johnson, Neyman beats discretization. A lot of methodologists have written against median splits for decades, and they've written against it because it's low power. I think that, at least I haven't found a paper that had made this point, which is, even though it's underpowered for testing an interaction, at least it's not biased by the nonlinearity. So that's a good thing about it. You won't get the wrong sign with the median split, but Gam, Johnson, Neyman will beat it. So that's a nice thing to know. I find this comparison interesting as a borderline case. So I'm saying, let's worry about the world being non-linear. Well, what if the world is kind of linear, the world, and I'm wrong, it's not really not linear. And we switch from Johnson-Neyman to Gam, Johnson-Neyman, from regions of significance to the Gam business. The loss of power is not enormous, right? You drop from like 80% power to 72% power. Does that make sense? So if you happen to study a phenomenon that is linear, and you say, I don't want to assume linearity, that's too strong. I'm just not let Gam do its thing, and I'll go with it. You lose power, but it's not an incredible loss of power. And if the model is not linear, you don't need to have a high false positive rate. You could also have low power. You can easily have low power with a linear model. And in fact, it's not hard to generate a situation where the median split will have more power than linear with the right nonlinearity in terms of detecting this. So my summary of this, my subjective evaluation is that there's no real downside in abandoning this technique that we've been using since 1930 something. Because even in the worst case scenario, we lose a little of power. We avoid false positive rates that are up the roof in many situations. And in realistic situations, even with a median split, we do fine. So that's where I say, you don't have to change anything. And here I would go from Johnson-Neyman to Gam, Johnson-Neyman.
Very quick question. Does it make sense to say, well, I want to test for nonlinearity? And if my test for nonlinearity is significant, I'm going to do the more complicated thing. If no, I'm going to do the simpler thing.
I would say no. And so the short end, like the more quantitative answer to your question, somebody asked me about that for this cell that comes here. And so what if you do a misspecification test, and only if you do misspecification, you adjust for it? And I have, in my simulations, I found it does help, but it doesn't help nearly enough. And intuitively, and this is a more generic answer that also applies to, like, should we test for normality and all that, the ability to detect the deviation from an assumption is not really indicative of whether the deviation is consequential or not. So you can have a very large sample, for example, and the deviation of linearity will be significant, but it will be inconsequential. Or you can have a very small sample, and you cannot significantly detect that it's not linear, but you're messed up anyway in terms of the. So I don't think that's gonna work. So that, can I move on to? And yeah. All right. So let's talk about this one. Okay. Why is this a problem? Why is it okay to compute the average here, but it's not okay to compute the average here? And I feel like this is a point that we knew in the 90s, and then the field sort of forgot. And I'm not sure why that happened. That if I look back at the textbooks that were referring to those 1990s papers, and they're kind of dismissive of them. So they mention them, but they're like, yeah, some people have said we should worry about this problem, but we don't think you really should worry. Or they say something like, the reader should exert caution. But, what does that mean? So it means that we ignore it. Okay. So, but here's the problem. If X and Z are correlated, and I'm going to show you a concrete example later on, then anything that's not linear in them will correlate with the interaction. And then we're going to have classic omitted variable bias, meaning what? We're omitting the nonlinearity, but we're including the interaction. And so the interaction is going to pick up the nonlinearity. So we no longer really get the average slope, at least not in the sense that we want to. Okay, so that's what this paper is about, and this is the third in a set of them. This is I don't think this is intuitive, right? I just said it. I think even if you read the words and you follow what I've said, and and I'm not being clear perhaps, but even if I were being clear, it's not intuitive. So I'm going to try to make it intuitive with figures. So in these figures, what I do to make it as intuitive as possible, I choose a dichotomous moderator, so we can easily see just two lines, right? If you think about it, if you had a continuous one, you would have like a 3D plot, which I have a hard time following. This, I just make up the data to make it as extreme as possible, and then I use real data that I have with Francesca. Okay. So let's say the true functional form is like this. That's the truth. That's it. There's no z. And the thing is, men and women have different x's. So this can be this example with work experience. So let's do that. Let's say women have a lot more work experience than do men, and this is a function of work experience. And so when you fit a linear regression to this curve, right, there's a missing term, right, the non-linearity of the x and the non-linearity of the z. Sorry, in this case, just the non-linearity of the x. And that's being picked up by the interaction. Why is that? Because it's saying, oh, women have higher x values. And because they have higher x values, they have a steeper line. So we estimate women as having a steeper line than do men, right? Even though they have the same functional, it's the same non-linear function. And so when we estimate just one linear function, it estimates two different functions. Let me say that again because I messed it up. We have one true function, but it's not linear. When we estimate a linear function and we force it to be linear, we end up estimating two linear functions. You can think of it as, I don't know if it helps, but it kind of makes it cute, as a Simpson's paradox, right? In the sense that it is never true that they have a different slope, but women have more observations in the portion of the slope that is steeper. And so the average woman has a steeper slope than the average man, even though the slope is always the same. We can think of it in those terms. All right, so this is the one that hopes to convey the intuition. And this one hopes to convey that even though this is extreme, you don't need an extreme example for it to matter. Therefore, if this is not clear now, should I clarify anything that I said? No, we're good. All right. So now I'm going to have this is real data. This is from applicants to a business school, and we have how many months of experience they have, and then this is a model that's estimated for them combined without differentiating whether it's men or women. So we know there's no difference between men and women because it's a fitted model, and it's what interview score they get. So I showed you this before. And what we see is applicants get a higher score as they get more experience. But it flattens out eventually, so it's not linear. And what we have here is, and what I like with this example, if you just look at the distribution, like this is showing how many, so those blips that you see is people giving like exactly 3 years of experience. That's why you see those blips. They're rounding the numbers of years. And 5 years, right? Just by looking at it, you can't quite get the fact that men have more experience than women. On average, they have 5 months more of experience. It's a very subtle effect. And in fact, the correlation between gender and experience, it's 0.06. It's significant, highly significant, but it's 0.06. So going back to your question, Yoel, you can imagine, you said, we look at the correlation, it's 0.06. So we're going to ignore the issue with non-linearities because it's so minimal. Okay, but what's going to happen? Because there are more men here versus there, we're going to get a flatter line for men than for women. Because the average, the Simpson's paradox again, even though they face the same slope, they're going to face a lower one, right? They're going to on average have a flatter slope. So what I did is to try to figure out, okay, how often, if you were to get this data, how often will you incorrectly conclude that men and women have a different return to experience, so to speak, right? So I'm going to predict what score do they get in the interview with how much experience they have interacting with gender. And I know the true effect 0 because I fit the model and I use the fitted model to generate the data. So I know the reality is no interaction. And I get an inflated false positive rate. But there's no way I would really be presenting if it was 6.2. It's 62%. You get a 62% false positive rate with that trivial level. And this is not me making up data that really forces the point. This is taking a data set where it happens. So what I just did is show you a stylized situation with a binary Z to make it intuitive, hopefully. Now I'm going to take published papers where the predictors continuous. This is one of the latest. As I mentioned, I've been working this for more years than I'd like to admit. I got a few emails from people after I announced the talk. Oh, remember you talking about this years ago when we met, whatever. So it's not a great email to get. Anyway, so I'm going to make Z not binary, and I'm going to focus on the, and it's not what I want to make. I'm focusing on papers where Z was not binary and where those authors were interested in the interaction. And what's interesting for our purposes is, because I've been working on methods for a few years, and a common comment from reviewers is, well, but a competent analyst will never do what you're depicting, right? So it's nice to have examples from people who are competent analysts that are doing this. So I'm looking at papers who were written by experts who are writing about interactions, but their interactions were invalid, right? So it's going to be hard. I think it's a harder argument to make that, look, nobody would do what you're saying they do if they do it. Okay, so I'm going to show two examples of them. Now, what both papers did was neglect what those papers in the 90s told us, which is if X and Z are correlated, it's bad news. Watch out with that interaction. Okay, so this is from probably the most cited tutorial on how to interpret interactions. Like a peer review tutorial. The textbook that I mentioned before had 10 times as many citations, but it's not peer review. So they have just one example in this paper on how to probe interactions. And that single example involves about 1,000 kids, and they're predicting how they do in math with an antisocial rating and a hyperactivity rating. I'm not super clear on exactly what they measure, and I haven't gone back to the original source to figure it out. But I think we understand roughly what's being measured there. And this is the table that they have in their article. And I got the data set and got it exactly right. So it definitely reproduces, it's the same data set. And this, they say, look, what you do is you project one standard deviation above, one standard deviation below, you plot it, and that's how you probe the interaction. But we're still looking at testing. So I'm not looking at probing yet. I'm not going to do that. I'm just going to ask, is there really an interaction? That's what I'm going to be asking. Before we probe it, do we establish there really is an interaction? So that's why I'm focusing on testing, still in testing. I don't know if that was clear. Okay, so the interaction is invalid if the X or Z are nonlinear, like we saw before, and they're correlated. So let's go like sort of step by step. So I take their data. This is the association between X, hyperactivity, and math. It takes discrete values, so it takes some guesswork, but I would not describe that as linear. I would describe that as what I like to call canopy effect. It's like a ceiling that affects just one variable. So it seems like if you're very hyperactive, it's bad for you, but if you're between 1 and 3, it doesn't really matter. So that's not linear. This one is more iffy whether it's linear or not. Kind of depends how much averaging you feel comfortable doing. I would say it's kind of linear. Maybe it's escalating a bit. Is again, you answer your question. It'd be hard to say, is that not linear enough to worry? It's hard to know. But this one, I feel more comfortable saying that's not linear. And so are they correlated? Yes, they are correlated, right? So this is one predictor, this is the other predictor, and they're correlated 0.504. So what we would expect, it's they have a version of omitted variable bias, so that their interaction is going to have a high false positive rate. So I compute the false positive rate for their interaction, and it is 30% or 31%. So if you do a linear model on the data that Preacher et al. Used, you get a 31% false positive rate. If you do robust errors, nothing happens. And then if you do any of the 3 solutions, if you add the quadratic terms like the papers in the 90s suggested, if you do the sort of this stronger, when I'm using, you'll see why I'm proposing using this. you say it's going to be x squared and z squared, but I'm going to compute it separately for the low values and high values to give the function more flexibility, you also get a 5% false positive rate. And for GAM, you also get a 5% false positive rate.
Yuri, how are you computing these false positive rates?
What I do is the following. I fit the data with a model that does not include the interaction. I think what I did here is literally doing fixed effects for every possible value here. So I have a model that I know does not depend on the interaction. And then, does that make sense so far? And so what I do is I get the residuals and I just shuffle the residuals. So I get new data. It's a little technical, so that's why I skipped it. But I shuffle the residuals to that model. So I know there's no interaction because the data is generated with a model that doesn't have an interaction. But it's as similar as I can make it to the true data because it's fitting the data, just missing that term. It's a version of like bootstrapping under the null. Right? I'm forcing the null under data, and then I'm asking how often do I get that effect. That's the same way I did the false positive rate for my paper with Francesca. I took the model, I fit it without gender interaction, I shuffled the residuals, and then I estimate the model with the interaction. Make sense? Okay. So that's one. The second example that's similar to this one.
So Yuri, can I say something that
yes,
just
please.
Very quickly, because I know those authors, I know that data set. I'm actually surprised they didn't do quadratic regression. So when you do, I'm a longitudinal researcher, you do within, you have functional forms, you're going to look at this data and it's going to suggest to you, at least in the first panel, that there is potentially a quadratic situation going on. So I just, nothing other than being somewhat surprised, because I think for a while that would be like, if you're looking at within data, you would say, I need to test a quadratic in order to make sure I'm capturing what's happening in this. So I guess I am a little bit surprised, because I feel like that has been a standard for a long time, at least in studying within data.
So a clarification question for you now. When you say testing the quadratic, do you mean including the quadratic terms and then assessing whether those are significant? Is that what you mean? Or?
That's what I mean, including the quadratic, in the regression.
But then only keeping them if they're significant. Is that right or no? Or
no,
are they kept regardless?
I think I would say regardless, but I guess you're right. Some people would drop them because they don't want to interpret the quadratic. I would say that's a common thing. People are like, oh, it's not significant, so I'm just going to drop it and I'm going to talk about linear.
Yeah, so I don't know. I think you probably come across more of those papers than I would in your, based on what you are describing. So I don't know how common it is. And it could be, to be clear, I'm not implying that these authors wouldn't know better, right? So part of me is, it's a bit conflicted about using their example, because it could be that they decided to make it as simple as possible. They didn't see this paper as a paper on really understanding the relationship between antisocial and math scores, but simply about conveying to people how to use interactions. And so they took that like as a poetic liberty, kind of just for clarity, like we do all the time when we teach. But on the other hand, so like in no way I think reflects poorly on them. On the other hand, if you're a student and you read this paper, you will not learn that this is important, right? Like none of these tutorials on probing interactions mention the issue of correlated predictors. So I think it's I don't think the general wisdom out there incorporates that factor.
Yeah, that was going to be the other point I was going to say. This 0.504, especially hyperactivity and antisocial, they should have expected pretty high correlation. And I think that's going to be a really important point, and especially that you're making. This is so common in correlational data. And because we're looking at things that are generally correlated, we just hope they're not too correlated. And 0.504 is leaning toward too correlated to be looking at. But I mean, I think that's such an important point.
Yep. But I would just go back and say, that's true. Pi 4 is a lot. I'm going back, but this was 0.06. So one has to worry a lot about that. Okay.
Yuri, one more while we're on this. There's actually a question in the chat about, can you say something about the relationship between the degree of correlation between the predictors and the false positive rate? Like, it doesn't seem as simple as, the higher the correlation, the more you really have to worry, because of this example that you just showed.
Yeah, I think so. That's not my personal strength, but I think many people could easily derive the following, like a version of the omitted variable bias formula for this. So and it would come back to some expression of the deviation between linearity and the true functional form multiplied by this correlation, right? At least if we're waving our hands, it will come to the non-linearity times the correlation. So you could have very high correlation, but if it was sufficiently linear, it would be fine, and vice versa. It would be the product of the two.
As the correlation increases, X and Z become the same variable, so it just becomes a quadratic instead of an interaction.
That's right.
So
That's
we
right.
shouldn't be surprised to detect it.
That's right. Yep. And that's precisely it. That's great, because that's precisely the intuition for why the interaction is picking it up. Because the interaction, when they're correlated, it behaves a bit like the quadratic. That's exactly right. And those papers that I was referring to before, they make that super clear. Yeah. Okay. So the other example, it's much more recent. This paper, actually, I learned of it the day before I first presented this work. Somebody sent me this paper, and I thought they had done the same thing I was working on, but they had already published it. And they had done an incredible job of, they reanalyzed something like 40 data sets in political science. So it was at the same time motivating and demotivating, right? So I was very happy that, in a way, relieved that I had to work on it. But then I realized that they hadn't considered this issue of the correlated predictors. So they deal with nonlinearities, and all their solutions work great for experiments, but they don't work great for observational data. And they have a few of those in the data set. So I chose this one. This is the only one I've reanalyzed in their paper, because they talk about nonlinearity specifically. So it seemed like a reasonable one to choose. They're looking at elections worldwide. It's a bit of an unusual regression. They're trying to predict how many parties will compete. So I guess in the US, there are many parties. We just hear of 2 of them, but there are many. And then how closer to election, how many presidential candidates there are. I'm not a political scientist, so I cannot quite work through the logic of the theory, but there are many papers studying this kind of question. So I want to make a point. Himmler, this authors, their paper is about probing. It's not about testing, and I'm still in testing mode. And what they're worried about is, if you're probing and the interaction is not linear, will you get it wrong? Okay. So I would say up to this point, I'm just adding to what they did. I'm not really second guessing it. But when I get to the 4th cell of my table, then I will come back and second guess them. But just to be clear about what it is that I'm doing in this particular demonstration. Okay. Right. So when we get here to probing non-experimental data, that's what they do. And that's what it's going to get really, really bad. Okay. So we know that the interaction will be invalid if they're not linear and they're correlated. Here are the functional forms from flexible models that I get, just to summarize the data. I'm not claiming this is the true functional form. I'm claiming it's plausibly not linear. That's all I really want to convey with this graph. Plausibly not linear, plausibly not linear. Correlated 0.7. Compared to Palm's point, there'll be a very high correlation. False positive rate, right? So how often do they get a false positive interaction that there isn't there? And that's just 100%. So if you fit a linear model to their data from this methods paper, you get 100% false positive rate. Robust errors lowers it all the way to 99.9%. Here, and this one is really annoying, because I would like to be able to say, just do quadratic and you'll be fine. But it's 70%. When I took that extra step for flexibility and I split the data and I allow quadratic for low excess and quadratic for high excess, then it looks fine. And even the gun doesn't look great. Okay. So far, the only one that's winning there is that one. Okay, so we're still here. I'm going to take a step back to see where we are in the bigger picture. I'll give you 2 examples that we're trying to convey the intuition. 2 that show real people who are very competent looking at real data have 5 positive rate. Linear does pretty bad. And among them, the interactive quadratic seems to be best. But I have just 4 data sets that I'm using to evaluate it. So I'm going to try 200 of them now. And for now, that I'll turn to simulation. And I'm a little bit tight on time, but okay. So I generated 3,840 scenarios. So what do I mean by scenarios? I'm going to generate data that's not linear. That depends on these two factors. There's no interaction, right? It's just X and Z separately. And they're going to be correlated. And so it looks like this. I say, okay, in this particular scenario, it's going to be X is going to be skewed this way. And the relationship between X and Z will be log linear. And the effect of X and Y will be cubic. And the effect of Z and Y will be log canopy. That's one scenario. There's 3,840 of those. Okay, that takes a while to run. So the first time, like a year and a half ago, I ran all of them. And then I realized there's really no point. I can just run a random sample of them. We learn the same in a fraction of the computing time. So I generated 3,840 and I ran 200 at random of them, around 1,000 simulations. And I asked if the data looked like this. So this could be like the pre-trained, but I'm just generating it. What happens? Okay. Here are the results. Let's parse it. Here are the 200 simulations, the 200 scenarios that are run. Here's how often the interaction was significant, even though there's never an interaction. And we have the multiple techniques. So let's start with the red line, the solid red line. That's the linear model. It does really poorly for the vast majority of cases. Again, robust and errors don't do anything. This is, I think, interesting. The median split performs very poorly here too. Okay, so if you run an interaction of X with a dichotomized Z, even a dichotomized Z, it's bad. I don't think this is intuitive. I think people will have the intuition that it'll be fine. In fact, Miller et al., they have the intuition this is fine. And they recommend people to dichotomize the moderator to avoid problems with non-linearities. So what's happening? If a dichotomous moderator is high, it's still going to be highly correlated with X. So when that's high, X is higher. And if the slope for X is different when it's high and low, you still get bias. It doesn't really help with the bias. So even though when you think about it a little, and even when you think about it a lot, it feels like that should fix it. It doesn't. It does not fix it. This one's also very surprising. And this stole like 4 months of my life because I thought GAM would be a solution to everything. And the GAM like this, I allow X and Z to be as flexible as they want, and then the interaction. And it has a really high false positive rate. And so I thought I was doing something. I play with it. There's a lot of free parameters you can adjust. I don't know exactly why it is so poorly. So I went back to the book by Wood, the person who wrote the article on the package. He talks about how GAM doesn't take into account some flexibility when fitting it. And so the standard errors are a bit too small, that the p-values are a bit too small also. But I don't think, my intuition is that that's not what's happening. My intuition is there's something wrong with in the computation. Like my guess is it's closer to a coding error in the package. That would be my guess. I don't know. I emailed Wood, but only like 2 weeks ago. In any case, we cannot use this, right? We cannot use this specification. That makes sense. We cannot use it. But I tried something. This is very recently. Instead of trusting the standard errors that GAM produces, I bootstrap them. And I only have 5 minutes. So I'm not going to get into details of how you do that. And then it's pretty good, but you are still in the 10% range. And this is asking a lot from the researcher, right? So say, switch to GAM and then do a bootstrap. So it's a lot to ask. And then you get still a 10% false positive rate. It's not great. All right, so that's point number 5. Number 6, do what the 90s papers did. Just add a quadratic. That worked great almost always. There's a handful of scenarios like that. Now, does this happen in real life? I don't know. It happened with Miller, right? So I'm going back. Miller had a high false positive rate for the quadratic. This is that part of that simulation that is rockets up. So it doesn't happen 0 times. But if we're making bets, right? Like if you have to take a gamble with your data, if you cannot go all the way, like, sorry, I'm gonna say a number 7 works amazing, right? This is not cheating. And this is, I'm not assuming the true functional form. On purpose, nothing that I simulated was quadratic. It's never quadratic. and it's never interrupted, quadratic. And yet it's perfect. It's right up, it's just flat.
So what exactly, Yuri, what exactly are you doing in the interrupted quadratic?
You say, okay, you're predicting y with x and x squared, but you allow, like imagine you had a linear regression. Let's make it simple, x, and say, well, if x is above the median, I'm going to allow for a slope change. So I'm going to predict y with x and then interact it with whether x is above the median. So you allow, maybe the slope is different when it's high versus low. And you do that both for the linear and for the quadratic, that's it. Right? So it's completely atheoretical. I tried this very late because I had no reason to think this would work. So I didn't try it until very late in the process. But at least for everything that I threw at it, it works great. And it's the nice thing, if you compare it to like bootstrapping again, this requires creating 4 variables. And then you run a regression that you can apply all the toolbox that you have now. Like if you're doing multi-level or if you're doing something, you can just apply all of that tool that already exists, all the packages that already exist, you apply it to that. So that's I find that very promising. And I don't think I have time for this one. So I'm just gonna skip it and say probing. Maybe I'll just show this. I have 2 minutes. So I'm not gonna do a horse race. Why am I not doing a horse race? Because the only thing that will work is Johnson-Neyman. And nothing else will work if you want to probe the interaction. And so I'm just gonna have one example that hopefully will persuade you that, or you will find why I'm wrong and you'll tell me why I'm wrong. Right? But this is the crutch of my argument for why Johnson-Neyman is the only solution. I created an example that it's completely made up of data, but it captures something that's fairly realistic. Right, so let's think of happiness, age, and wealth. And so what I'm going to do, forget the function, doesn't matter. People are happier in middle age, less happy when they're older, less happy when they're young. That's roughly what we know. And people are happier if they're wealthier. That's probably true. That is true. But there's no interaction in the real model. But wealth and age are correlated, which happens to be true. In real life, wealth and age are correlated. If you do simple slopes, it looks like that. This is trying to estimate that. That's really bad. And if you do GAM simple slopes, it gives you that, which looks pretty good. And then if instead of doing simple slopes, I do what that Heymiller paper proposed, which is, and I realize I have 1 minute, so I'm gonna have to kind of rush through this picture. What they proposed is say, look, to worry about non-linearities, you can do 2 things. You can say, they said, so one thing they do is instead of plotting Y, they plot the marginal effect the way Johnson-Neyman would. So what is the effect of X for different levels of Z? What is the effect of H when wealth is low, when wealth is high? They say to get this right, what you do is, sorry, 1 sec. This is the true marginal effect. It's constant with Z because there's no interaction. The effect of H does not depend on wealth. That's the truth. This is the wrong answer given by Johnson-Neyman. And it's the same answer given by the estimator that Heymiller proposed, which is dichotomizing for the intuition that I used before. If it's correlated, a dichotomous variable is also correlated. And moreover, it's just as wrong. It's not helping at all. And if they have a kernel estimator, which is just it's a fancy way to estimate things fluidly and flexibly rather, it takes a while to run and it doesn't give you any improvement over the linear model. And that's Johnson-Neyman. So to me, that like once you start here, like should I really run 10,000 simulations with 500 scenarios? I feel like maybe you can kill it, and if you kill it, we give up on probing interactions. But this seems like a fairly promising solution, and I'm 1 minute over.
You're real quick, just for the everyday researcher. Charlie Dorson had asked this question earlier, like, how does the everyday researcher run GAM Johnson-Neyman? Like, how hard or easy is that to do?
It's pretty easy to do, and I plan on creating a R package, and it'll be called interaction gate unless somebody steals a name before I do it, and then it'll be particularly easy to run. But it's really not that hard. I would say it's like 3 lines of code to run for experiments. For experiments, it's very easy.
Great. Okay. Well,
if you want to get the paper, that's a link.
Oh, great. And maybe I'll also put that in the YouTube notes or whatever.
Okay.
When we post the video online. Okay. Well, Yuri, this was really great. I've seen this before, and yet I still learned a ton. And I'm sure everyone else attending did as well. Thanks to everyone for joining us. We won't be back next week because of Thanksgiving, but we'll be back the week after. So enjoy your weekend and your holiday. Take care, everybody.